So we're now going to talk about the network, but before diving into the network, I wanted to quickly clarify how GAN works. So you have two models. On one side, there is a generator, which can generate images from a random noise. And on the other side, there is a discriminator, which is fed with the generated images, but also with real images. And it tries to classify the images into being fake or real. And the loss of the discriminator is propagated in the generator, which allows to train both networks. But since the objective of the two networks are the opposites, the loss used to train the generator is the negative of the discriminator's loss. And the generator and the discriminator are training together, trying to beat each other. So we can now approach our network. So the main idea here is that there is a generator on the left, which generates text boxes, and a discriminator, which tries to make the difference between real and fake text boxes, which is the common pattern of a GAN, as we saw in the previous slide. And the generator takes as input a word, which is encoded in the word encoder, but we'll discuss this part later. And it also takes as input a normally distributed random noise, which is encoded in the latent encoder. And this feature of the latent encoder, it actually comes from the GAN paper. And what it does is passing this noise into a succession of dense layers to output a style vector. And this vector controls the style of the text box. So for instance, the font, the color, or the texture. And both the word encoded and the style vector are given to the synthesis network, which generate the text box through a series of deconvolutions. And the output of the discriminator, shown here, actually allows to compute the GAN loss. And this loss is propagated both in the discriminator and the generator, as we saw again in the previous slide. Finally, to make the generation of readable text possible, we plugged in an OCR, shown here, that reads the generated text box. So we use a pre-trained OCR called Aster, of which the weights are fixed during the training phase. And a loss can be computing from the difference between what the OCR reads from the text box and which word it was actually supposed to read. And this loss, is propagated to the network, which allows to train the word encoder. So to sum up, on one side, we have the GAN loss to ensure the generated text box looks like a text box. And on the other side, we have the OCR loss to ensure that there is the right text on the image. So we're now going to talk about the losses. So first, the OCR loss. So the OCR's output is called logits, which is a 2D array where the first dimension represents the characters found in the text box. And the second dimension is a score for each possible characters, representing how likely it is to be this character. And we have two possible losses for the OCR loss. The first one is softmax cross entropy, which is computing between the OCR's output logits and the ground truth. And the other one is a mean squared error, which works a bit differently. Because to use this loss, we need the real text box to have the same text as the generated text box. And we are going to basically infer both the real and the generated text boxes in the OCR and basically compute the mean squared error between the two logits found. And doing so, our classification problem becomes more of a regression problem because the objective is not anymore like in the softmax entropy to write the perfect text, but rather to write the text as it is on the image. So for now, just keep in mind that we can use both losses, and we'll actually discuss the results obtained for each loss later on. So the GAN loss is the second loss, which uses a soft plus. And the soft plus behaves a bit like a rule, but so rectified linear units. But the main difference is when the x is near 0. And we use the results outputted by the discriminator to train both the generator and the discriminator. But since the objective is the opposite, when considering the loss for the generated text box, we need the minus sign here, which is not present there. And only the discriminator takes into account the loss for the real text box, as shown here. So I just wanted to do a quick recap of what we've seen so far and what is still to be seen about the network. So first, we thought that first we had an overview of the different steps of the network architecture, and then we discussed more in depth the losses used to train the network. And now we're going to talk about the word encoder and the different tricks used to handle words of different lengths. So as I just said, let's now dive into the word encoder. So it takes as input a word and output a tensor. And each character of the word is considered individually. So the number of characters actually represent the batch size. And we first obtain an embedding for each character. And each of these embeddings goes through a dense layer, increasing their size. And at the end, the characters encoded are concatenated while preserving the order. So first there is the vector responsible for the H, then the tensor responsible for the E, etc., etc. And since the synthesis network requires a fixed size input, we need to fix the maximum number of characters the input word can have. And when the number of characters in the input word is less than this maximum, we pad the output tensors with 0, which is the padding shown here. We also need to adjust the length of the text box outputted by the generator because it has a fixed size, and depending on the number of characters in the box, we want a different width. And since we know that a word contains a maximum of n characters, and each letter corresponds to 1/10 of the width, we can crop the box accordingly. So these were actually the original text boxes, and they have been actually cropped according to the number of characters in each word. Because here the n is equal to 8. So here we kept 5/8 of the boxes, here 4/8 of the boxes, and here 2/8 of the boxes. And doing so allows for two things. First, there is no distortion. So for instance, here, the network is not trying to stretch a word with 2 letters into the entire width. And secondly, the discriminator does not choose the residual noise as a pattern to make the difference between generated and real text boxes. However, the disadvantage is that it kind of forces some ratio to be fairly constant, such as the spacing between the characters or the size of the characters. Let's now talk about the datasets. So the datasets used are MLT17 and MLT19, which are composed of fairly simple text boxes with printed characters. And prior to training, we infer all the text boxes of the dataset in the OCR, because this allows to reject the boxes for which the loss is too large, because such boxes correspond to error, such as boxes in the wrong direction shown here. And after this filtering step, around 75,000 boxes remain. So we classify the characters depending on their number of occurrences in the data sets compared to others. So when this ratio is equal to 1, it means the characters appears as often as others. And for instance, here, these characters appears less than 10 times less than other characters. And as you may have guessed, this distribution actually follows the character distribution in Latin languages. But the disadvantage of this heterogeneous distribution is that if we only use words from these data sets as input words for our network when we train it, then our network will be very bad at generating these characters. So to overcome this issue, another text dataset was used, which is made from a Wikipedia corpus and an English dictionary, which allowed basically to have more input words. And when building the new dataset, we ensured that every new word added contained the character currently occurring the least in the dataset, so that we could have a much more homogeneous distribution at the end. And we also use these corpuses to build the validation and test datasets to validate and test the OCR loss. Also, note that this corpus dataset cannot be used when training using the mean squared error, since it requires the text box with the same text, which we don't have here. So to emphasize the importance of using this corpus dataset I just showed, we pre-trained 2 models, one with the copies datasets and the other one not using it. And both these models were asked to generate a word made of the characters currently occurring the list in the datasets. I mean, the data occurring the list in the datasets. I mean, these characters, which were the characters shown here. And in the first case, it was asked much more often to generate these characters during the training phase, since they appear much more often in the copies datasets. And as you can see, it's now doing a much better job at generating them. Here we can barely recognize any of the characters. We're now going to talk about the results. Again, we pre-trained the model on 4 different configurations. The first pre-training used the softmax cross entropy as the OCR loss, so these 3, and the last one using the mean squared error. And the difference between the first 3 trainings is how often the copies dataset we just discussed is used. So either not at all, once every 4 inputs, or once every other inputs. Also, note that even though we train with different OCR losses, the validation metric is always the softmax cross entropy, since it really is an indicator of whether the text is readable. And as you can see, when training with the mean squared error, the softmax cross entropy is about 5 times larger than when actually training with the softmax cross entropy, which basically means that it is 5 times worse at generating words. And here are actually a few examples of word generating with the first and the fourth model, so with the softmax cross entropy or the mean squared error. And in the first case, so the softmax cross entropy, you can see that the words are neat, correspond to the input word, which is not really the case when using the mean squared error. For instance, if you look at Evinci, like it wrote it well for the softmax cross entropy, but it's not really the character we were expecting in this case. This graph represents the generator and the discriminator losses for the training, for the same training that I just showed you in the previous slide. And as you can see, these losses oscillate quite a lot in the first few steps. Sorry for the little blank here. So yeah, I was saying that this training oscillates quite a lot in the first few steps before stabilizing at the end. And ideally, you should have the discriminator and the generator losses to be around the same value for a stable training. But in our situation, when training on a larger number of steps than shown here, the discriminator consistently ends up beating the generator. So the lower the loss of the generator at the beginning, the better. This is why we actually prefer the light blue curve to the orange one. So you can't really read it here, but it's actually using the copies dataset once every 4 inputs rather than once every other input. And from the results obtained on the previous slide, we pre-train a final model, which uses the softmax cross entropy as the OCR loss and takes input word for the copies dataset once every 4 inputs. And we computed the test loss. And to do so, the test dataset was inferred 100 times the model, which led to an average of 6.38. Note that since we use random vectors for the style, the test loss is not always the same, which is why we need to get an average. And as a mean of comparison, all the images of the dataset were also inferred in the OCR, which led to an average loss of 1.27. And there is quite a noticeable difference between these 2 losses, which is mainly explained by the fact that some style vector lead to hardly readable text boxes. So the model was asked to generate the word generate at different training steps. And I quite like this video as it really shows how the network learns to write. So at the beginning, it's just random noise. Then you slowly start to see some shapes that look like characters. And then you can finally see the word it was actually trying to generate. And there is something quite interesting to notice from this video, is that if you go around here, you can see that the model first learns to generate the letter A with this shape, which looks a bit like an O. And sorry, I restarted it. And as the training goes, it changes the way it generates the letter A. Oh, sorry. I'm going to try to stop it at the right time. Yeah, here's a good one. So it changes the way it generates the letter A, because now this shape cannot be mistaken with any other letter anymore, which is the result of using the softmax cross entropy as the OCR loss. So let's now see how to control the style. So as we now know, the latent encoder, so this part here, uses a random vector to define the style of the image. And so using a different vector means a different style, and reusing the same vector means reusing the same style. So as you can see, we can write word with the same style. And this picture actually emphasizes one of the main limitations of our network, which we already saw with the letter A in the previous video. It is that changing the style has a weak effect on the shape of the characters. You can see that all the A's are kind of shaped the same way, even though there are many different ways to form an A. And it's similar for all the other characters. But this behavior is partially explained by the fact the dataset uses printed characters which do not vary a lot. So the final thing I wanted to show you is this slide that you probably remember from the introduction. But what I did not tell you before is how to extract the style from the original text box. So it's a concept that was borrowed from the GAN paper again. And what we're going to do here is generating a text box with the same word than the one on the original image, and train the style outputted by the latent encoder to make the generated text box as similar as possible as the original image. And then we can reuse this trained style to write new words, as shown in the last two lines. So in conclusion, the results obtained are satisfying since our model manages to generate readable text boxes, which are matching the input words and with various styles. However, there are a few limitations. The main one is probably that changing the style vector does not significantly change the shape of the characters. So training an OCR only with data generated with our model will probably not make it generalized enough. Hence, our model may be more appropriate for data augmentation. So training with a mix of generated and real text boxes, of course, at the risk of creating a bias towards some character's shape. Luckily, there are a few axes of improvement to overcome these limitations. The first one will be to think about training using both the mean squared error and the softmax cross entropy. Because when using the mean squared error, the objective is not to write a perfect word, but rather to write the word as it is on the real text box. So doing so, we could maybe allow our model to generate printing characters with different shapes when changing the style. Another way to improve the network will be to use a dataset with fancier characters. And if we combine that with the addition of a recurrent layer in the word encoder, we could maybe generate link characters. And so in a nutshell, TextBoxGan could probably generate diverse and unbiased text boxes with some improvements. And hence, it certainly has the potential to train OCRs in a better way than the synthetic dataset I showed you in the introduction. So here's my contact if you want to reach me after this talk. And here's the link to the GitHub repository that I told you about at the beginning. So there is pretty much everything I've told you today and more, of course. And there is also, if you want to try it yourself, a Docker file and the make file as well to download the datasets, as well as download links for the models. So you basically got everything to try it. So thank you very much. And do you have any question? All right. I think there is a bit of majority of French people. So if you want to ask your question in French, feel free.
I think I have one question for you. You discussed like the encoding the characters in your network. If you can go back a bit in your presentation, I think it was like in the middle of the,
This one?
Yeah, this one. So instead of using like a single character encoding, could you have maybe try to do some kind of, I don't know, bigram embedding for your characters? And by doing so, you may be able to, I don't know, grasp connections between characters, for instance.
So you mean using an embedding that uses 2 characters instead of 1?
Yep, exactly.
That could be a good idea. So in the conclusion, I suggested the use of a recurrent layer to do these kind of things. I think it wouldn't really work because so there are about like 70 or 80 different characters if you consider special characters, capital letters, and everything. So you basically need to it's exponential, I think. But basically, like the number of bigrams will be too big for the number of data in our data set, and there will be like some bigrams which will actually never be seen, like I don't know, ZZ or Z dots, stuff like this. So if you want to generate them afterwards,
yeah, but
I'm not sure.
In your use case, like being able to augment the data in like other applications of OCR, would it be like important to have seen this type of diagrams, or I don't know?
I'm pretty sure, because either way, like there are just too many bigrams, and I think even quite common bigrams like O dot, for instance, it will be seen like once or twice in the data sets. So I'm not sure we have enough data to do this kind of approach. Okay. So maybe using a recurrent layer is more appropriate, considering the amount of boxes.
So what you're saying, like the number of elements in the vocabulary, like saying I don't know, 50 or so, maybe more, times 2, no, square, sorry, would be too much as combinations.
Yes.
All right. Okay.
Yeah. Yeah, because basically 80 squared is like 6,000, and you got like 75,000 boxes. So
yeah, because your test set may be a bit small compared to the amount of information you need to learn on the diagrams, for instance.
Yeah, but the test set is just an indication. You should be able to do anything afterwards.
Okay. Okay, got it.
It was a great question. Thank you.
Does it support non-Latin characters?
Not right now. I didn't train it with any. It could if your data set would use non-Latin characters, but
there is a question in the chat.
Oh. Oh yeah. So it's what I just said. So if you train it with a data set which is not using any Latin characters, then it could. But right now the data set, I think I can find it. It's only with Latin characters. But actually MLT17 and MLT19 contains a lot of non-Latin characters. But since I don't really understand them and I don't know how to read them, I couldn't be a good judge of whether my network would be good or not. But it definitely could.
No. Did you retrain your OCR model with the data you generated?
No, I didn't do any retraining of the OCR. As I specified in the conclusion, it's a good first step. So it's a good start to generate data, but right now it's too biased to basically generalize. So it needs the improvement, like the areas of improvement I started stating, but I haven't tried them, and I know that if I try them, it's not just implementing them. Like I will have to iterate a lot. So one day I'll do it.